Welcome to the Strategic Learning Wireless Networks Theory and Application, a tutorial 2 of week 2. So as you may have known, in this tutorial, we will be discussing the theoretical studies that have been followed from this week's lecture by Mehdi. So first, we would like to check what is about learning in the games and why we need that. So in the games, as you have noticed, there are several components interacting with each other. So the games are taken place in certain environments, and they have a couple of players involved in this environment interacting with each other. Each players have their own set of strategies that may conflict with each others. Based on their strategies and based on the environment, they will be rewarded with certain payoffs. So the payoffs function are going to interact with players' strategies and the environment. However, it is a bit hard to realize what are the interactions between these three components. Furthermore, if you think about these games, when we talk about decentralization, then there's a challenge about how the information among these agents are going to be shared. Again, then it comes a lack of cooperation, where we cannot always expect agents to communicate with each other and try to reveal their hidden intentions to each other. So basically, because of this lack of cooperation, the information between these agents are not shared properly. Then in addition to this lack of information, lack of cooperation, there will be agents that would try to use certain strategies for their own benefits. So they have certain tactical advantages of hiding their true intentions. Because of these facts, it is quite challenging to find the link between these three main components in the games. So ideally, what could happen is in this learning in the learning environment, what would happen is the game start in an initial state, then eventually agents would like to learn about their strategies, and finally they reach to a desired destination. So what are the possible learning architectures? Traditionally, the most conventional approach is this centralized design, where suppose these are agents and they would like to play certain strategies, come to certain agreement. For that, they would take a support from a centralized helper. So centralized helper will decide what each agent has to do to achieve the goal defined by either as a cooperative goal or a goal specified for individual agent. However, decentralized design requires communication between all the agents in the network. So depending on the information that required to devise a strategy, this communication link plays a quite a big role. As shown in this example, if the agents are kind of wireless devices with limited power supply and limited capacity between the centralized entity, lack of this communication link, the capacity of the lack of the capacity in this communication link would result in quite high latency in this learning process. This idea, centralized idea, could be quite suitable when we have quite a reliable link between the centralized entity and the agents. But when we go to the wireless domain, the centralized learning architectures are somewhat not favored, I would say. Then the second option would be the federated design. So here still we have a central helper and these several agents that would require communication with this central agent. However, now these agents have kind of intelligence, unlike the centralized design. So basically what these agents would do, they would try to learn what they have to do to achieve their goal, but eventually they require certain information from other agents, which can be accessed through a centralized entity. So the information could be raw information coming from other agents, or somewhat a representation of the raw information. So the centralized helper could help these agents to learn their strategies without taking the entire burden to centralized helper itself. Then when we go to the extreme case where we don't have a centralized entity, these agents needs to communicate with each other in maybe peer-to-peer fashion. So this we define as collaborative learning architecture. So in this lecture, at least we consider these two cases, federated and collaborated case, and as either decentralized or distributed. Although these terms have slightly different meanings, in this course, at least this context, we will use either decentralized or distributed architecture. So in this distributed learning architecture, it would be good to know about how much information certain agents could access. So based on that, we can consider about like two cases. Agents with full information and agents with partial information. When we consider about agents with partial information, they have access to the observation of their past. That's all. However, if we consider about the access to the agents with access to full information, similar to the other case, they have access to the observation of their own past, while they could have access to the observation of the past of the others as well. So ideally, we don't consider about access to the strategies that can be taken at the real time, which require communication links between agents. However, this full information consider about the strategies taken during the course of the history. So still, this means there could be there's a need of quite high communication capacity links between agents or through a centralized entity. However, when we go to the case with partial information, mostly this could rely on without communication between other agents. Let's go into details about this correlated equilibrium. So this correlated equilibrium is a solution concept, quite similar to the solution concept that we have discussed last week, the Nash equilibrium. However, this is more generalized compared to the Nash equilibrium. So here, players choose their actions based on a public signal. These public signals could be a suggested action or some additional indication, which could allow player to make a decision about choosing certain action. This suggestion in this public signals, but what is important to know is a suggestion for other players are not revealed to certain players. So a player A might see a signal. Let's say there is a kind of a coordinator and two players A and B. When a coordinator send a signal to player A doesn't know whether coordinator send a signal to player B or not. And even if we know B is going to receive a certain signal, it doesn't know what is the exact signal. So basically, based on the signal A received from the coordinator, A has to make a decision and pick a certain action. So now in this here we need to define a probability distribution profile over these suggestions, which we are going to use as pi, and it is a vector of a set of strategies. So these strategies are the set of strategies that are going to be selected based on this public signal. So this probability distribution profile is going to be correlated information, correlated equilibrium only. These recommendations are kind of self-enforcing. So means these a player cannot deviate from this recommendation. By deviating it, most likely player will has to pay a price. So formally, this condition is going to be defined here as like this. So you can see phi is a correlated equilibrium when, if you look at this right hand side, this is the utility into the probability. So the summation provides you the expected payoff. Right. However, you have to notice when player N plays this strategy Sn, and this S minus N is the notation that we are going to use all the strategies placed by other players. So you can notice that this Sn is fixed, while this S minus N can be changed. So this is the expected payoff for player N, given that player N is always using his strategy Sn, while all other players could change their strategy. This strategy, so this is what let's say this Sn is the choice of the strategy based on the public signal. So which means when the player N choose this strategy Sn, there's a possibility that all other players could take different strategies. So taking this summation, it will yield the expected payoff for following the recommended strategy. Now, if you look at the left hand side, you can see this is the same probability right here. So it means probability of playing choosing the strategy Sn while others are playing S minus N. However, you can notice here the utility we have used S dash. So it means this is the recommended strategy, and here, which means the player has deviated from his recommended strategy. From Sn to he has deviated to S dash N. However, others are going to play their set all the possible strategies. Now, what this inequality says, when the player N deviates from Sn to S dash N, the expected payoff is going to be either remain as it is or decrease. It is not going to improve. This is valid for all the players and for all their strategies. So basically, that is the condition indicating the self-enforcing requirement. So a deviation from the suggested strategy result in a loss of the expected payoff. One key important thing is, if a game is finite, it has finite players, finite set of strategies, then they have at least one correlated equilibrium. Unlike Nash equilibrium, because we found that in the Nash equilibrium, if we consider about pure Nash equilibrium, there is no guarantee the existence of pure Nash equilibrium. However, we notice in the mixed strategy Nash equilibrium, there could be there can be at least one mixed strategy Nash equilibrium, even that the game is finite. So similar to the mixed strategy Nash equilibrium, so a correlated equilibrium can exist when a game is given as a finite game. Now let's check this idea with one example. Okay, our first example is about the game of chickens. So rather going in terms of this name, I'd like to take an example from one movie, from an example from this Fast and Furious movie. So here, what happened is there are two main characters, Dominic and Shaw. They try to defy each other by speeding their cars to face. So they have like two options. They can decide to dare, or they can decide to chicken out. So if one dares and the other one chicken out, so the one who dares earns 4 points, while the one who chickens out receive points of 0. If both dares, as you can see in this example, what could happen is they crash with each other. So the loss is 2. So basically we can consider it as a payoff of -2, because now you consider about in terms of utilities. So this -2 payoff will be for the both players, not just single one. However, if they both decide to chicken out, they work out with 3 points. So the first part is to find all Nash equilibriums. Since you have already gone through during the last week, so I would suggest you to pause the video now and try to work yourself, and then join with me and we will see whether we achieve the same results. To find a Nash equilibrium, first it would be much easier to start with this come with this tabular form. So now we can write two players here, Dominic and Show. So both have actions dare and chicken out. Right? If they both dare, here the payoff is -2 for each. They both chicken out. The payoff is 3. Now one dares and the other chickens out. So the one who dares receives 4 points, while the one who chickens out receives 0. And similarly, it will be swept in here, right? Now first, let's try to see whether there are best responses that could yield to a single strategy that is going to be Nash. Now let's see if we start from here, there. Of course, in this case, Dominic can chicken out, which would increase 2 points for him. Similarly, Shaw can decide to chicken out. So basically, this is not going to be stable strategy. And if we consider about this case, chicken out and dare, of course, Dominic can't switch without losing. So he's going to stick in here. and show, he's not going to chicken out because it will be a loss of 1 point. So here he's going, this strategy is going to be one of equilibrium. Similarly, since this is just swapping these two values and this way of matrix is symmetric, we can consider this strategy yields another Nash equilibrium. And finally, this one, if you consider here, when both are chicken out, of course, one would prefer to select there that could improve their payoff. So this is not going to be a Nash equilibrium. So we have, let's say, one solution. Write it in here. Of not one, actually there are two. Either C comma D or D comma C. Those are the two possible strategies that yielding pure strategy Nash equilibrium. So this one corresponding payoffs of 0, 4, while the second one corresponding 4, 0. So these are the two pure strategy Nash equilibrium. Now if we check about the mixed strategy, so you can remember, let's put probability alpha here and 1 minus alpha here. So that means there's alpha probability that Dominic is going to use his strategy there as there, while 1 minus alpha probability to chicken out. So now suppose Show is using his the strategy there. So now we are focusing about the payoff of Show. Sorry. Right. So now first, let's write what happened if we use there. So if we use there, we know there's alpha probability. Dominic will use in there, resulting minus 2 points. And 1 minus alpha probability of choosing chicken out, which would result 4 points to Dominic. So that means we are going to end up with 4 minus 6 alpha. This is the expected payoff when for Show when he is using action there, and Dominic is strategizing his there and chicken based on the probability alpha. Similarly, we can write for the action chicken out the expected utility for playing action of C. In that case, if Dominic dares, the payoff is 0. If he chickens out, both chickens out, so it will be 3 into 1 minus alpha. Okay, now the choice of alpha would be the one that result the expected payoff playing there is equal to the expected payoff playing chicken out. So this is at Nash equilibrium. We have this condition. That means we have 4 minus 6 alpha is equal to 3 minus 3 alpha. So that result in alpha is equal to 1 over 3. Since this is a symmetric matrix, so basically we can consider Show is using the same alpha probability and 1 minus alpha probability for the chicken out, right? So now we can see, we can write, okay, the mixed strategy Nash equilibrium is held when either player use 1 over 3 probability for there, and 2/3 probability for chicken out, which yield a payoff of how much it's going to be? 2 points? Yes. So we have 2 pure strategy Nash equilibria and 1 mixed strategy Nash equilibria. Now let's move to the second part of this exercise. Okay, now in the second part, what is happening is there's a third party who is involved in this scenario. So here, Roman picks to send a signal to these 2 players. So he has 3 options. Say he has 3 cards. First, he cheers Dominic. The second one, he cheers Show. Oh, he can decide to do nothing. So there's the suggestion here is once a player is get the cheering, he will dare. Otherwise, he is not. As you can remember, this public signal intended for player Dominic is not visible to player Show and vice versa. That means when Roman cheers Dominic, Show doesn't see. So he can, what he Show can think, either Roman is cheering Dominic or Roman is doing nothing. Similarly, if Dominic doesn't see any message from Roman, that means either Roman decide to cheer Show or decide to do nothing. Now the question is to show that this approach yield a correlated equilibrium. Let's write the payoff matrix here. So Dominic, Show, they have payoffs, 2 different actions and corresponding payoffs. 3 and 1 who dares get points 4, and it is flipped in here, right? Now if we check about this choice, Roman cheers Dominic. Dominic decide to play dare. Since Show doesn't receive any signal from Roman, so he decided to chicken out. So they end up with in here. So this is when the card number 1 is displayed. This is the strategy that both players is going to play. In that case, Dominic received the highest reward points. And similarly, when Roman decided to cheer Show, then Dominic needs to chicken out. They are going to end up in here. Finally, if Roman decide to do nothing, so basically they are going to end up in this case. So okay, one thing I forgot to mention is that Roman picks randomly, but it is uniformly. So basically it means he has 1/3 probability to pick one of these 3 cards. Suppose like he has 3 cards, he randomly pick one based on that card. He decide what to do. If it mentioned it's cheer Dominic, he will cheer it. Otherwise, he will cheer Show. So for these 3 public signals, they have equal probabilities. Now the question is to show this approach yields a correlated equilibrium. For that, first we can pick Dominic will show without loss of generality because this is a symmetric matrix. Now let's focus about one player from here, right? So what we need to do is consider about, okay, what is the payoff when he follows the recommendation. Now suppose Roman cheers Dominic. Okay, so Roman cheers Dominic. In that case, the recommendation is to play dare. So we can find the recommended one is to play dare. Then we know show is not receiving any message, so he decided to chicken out. By doing that, the Dominic will receive points of 4. Now, okay, this is the recommended strategy. Now, what would happen if we deviate? So here, Dominic follows the recommended one. Here, he deviates from the recommended one. So when Roman cheers Dominic, if he decide to chicken out, what could happen is since show is chicken out, they ended up in here, right? This one. So basically Dominic will be receiving only 3 points, where he could have received 1 extra point if he have been stick with the recommended strategy. Okay, this is when Dominic see the public signal from the Roman. What happened when Roman is not cheering Dominic? Because why I mentioned it is not cheering, because there are 2 options here. The Roman can cheer show or do nothing. With with these 2 choices, what Dominic see is he is not getting any messages. So basically, from in terms from the Dominic's perspective, it is like he is not receiving any message. So in that case, the rule is he has to chicken out. Now let's see, when following recommendation, in here Dominic is chickening out, right? Then what is the payoff? Suppose there's like 50% probability that Roman has picked to cheer show, right? That in that case, Dominic doesn't see, like whenever Dominic doesn't see a message, there's a 50% chance Roman cheers show. In that case, we are going to end up with this case number 2. That means Dominic is getting 0 points. But the other 50% of probability, what happened is show is also going to chicken out because he doesn't see any public message. In that case, Dominic is receiving points of 3. Basically, it means 3 out of 2. This is the payoff. Payoff when the Dominic follows the recommendation. Similar to the last case, let's see what could happen if he decide to deviate. So whenever he deviates, so that means Dominic decide to dare, even though he doesn't see any message directed to him. So instead of playing chicken now he is going to play in here. Now we know this scenario. there's a 50% of chance that Roman might be cheering Shaw. So in that case, Shaw will be using his action to defy Dominic, and Dominic has now decided to deviate from strategy. So he is going to use the defy. So both end up with crashing, resulting in -2 points. That happens with 50% probability. And the other 50% probability, since Shaw is not receiving any public message as well as Dominic, Shaw will be chickening out while Dominic is defining. So in this case, he get 4 points. Now if we consider about this one, this is going to be 2 minus 1 is equal to 1, right? Now you can see, if Dominic decided to stick with the recommendation, he could have get 1.5 points, while deviating has cost him 0.5 points. So of course in here we notice deviating cost him a point of 1 when he could have the maximum payoff. So ideally in this situation, naturally a player doesn't want to deviate, because he know this is the exact strategy that is going to result the maximum payoffs. So basically deviating, of course, is not going to get anything more out of it. However, in this case, we notice that, okay, there are some cases that Dominic might end up with zeros, while some cases he might end up with 3. So that is why he decided to change his strategy, hoping he would get into this position by deviating. But we notice with the given this 1/3 probability of picking up these actions, what happened was Dominic has lost about 0.5 points by deviating this strategy. So basically that means Dominic preferred to follow the recommendation. Since this is a symmetric payoff matrix, we can consider same argument is valid for Shaw, and he will also prefer to follow the recommendation. That use the idea that no player would prefer to deviate from the recommendation, yielding a correlated equilibrium. Okay. Now it's time for one more example. So in this exercise, we are given the payoff matrix for 2 players. Player A has 2 strategies playing U up and down, and player B has playing left and right. So as you may notice, this is also a symmetric matrix. And the question is, first part is to find the all pure and mixed Nash equilibria of following game. Okay, first we will solve that, then we will go to the second point. That if we decide, okay, nobody is going to stick in this one because both players have the opportunity to improve their payoff by deviating. When we pick here, player A prefer to stick with this choice because this will result in a loss. Deviation of this strategy result in a loss, whereas for the player B also it is going to be a loss. So this is going to be a Nash equilibria. Similarly, this choice is going to be Nash equilibria due to symmetry. And at last, this choice, of course, we can see player A prefer to deviate to improve his own payoff. So this is not a Nash equilibria. So at least we can consider the pure Nash equilibria is resultant in two choices, down, left, as well as up and right, where the payoffs are 3,6 and here 6,3. These are the mixed Nash equilibria. Now, if we consider, sorry, these are the pure Nash equilibria. And now, if you check the mixed Nash equilibria, you can simply consider about this as alpha, this as 1 minus alpha. In order to find to achieve a mixed Nash equilibria, what needs to done is expected payoff of playing left should equal to expected payoff of playing right. This is the condition. Now, if we consider about utility of left, so it is 0 into alpha, 6 into 1 minus alpha. Here, if the player B decide to play right, it will be 3 into alpha plus 5 into 1 minus alpha, right? So basically, this means 1 minus alpha, 1 for alpha, and alpha should be 1 over 4, right? Yes, so we know since this is a symmetric matrix, we can say player A picks up with 25% probability, player B pick left with 25% probability, and the payoff, expected payoff for player A and player B is going to be this here 3 out of 4, so 9 out of 2. Yes, so this is the mixed Nash equilibrium. Now let's move to the part 2 of this exercise. So here find a correlated equilibrium such that sum of payoffs over both players at CE exceeds that the sum at any Nash equilibrium. Okay. Now if we consider about this part, sum of payoffs over both players. Now if we consider about all three cases here, sum of payoffs of both players would be, so here also it is 9 out of 2, at least all three cases we end up with, okay, this utility A plus utility B. So here, although I write utility, this is the expected utility, right, for the mixed strategy phase. Otherwise this is for exactly this choice of strategy, one of these choices. So anyway, all these three yields that the sum of the payoffs is equal to 9. Now the question is, we need to find a correlated equilibrium such that this at the correlated equilibrium, the sum of the payoffs exceeding this point, 0.9. Now, if we think about the case where what could be a public signal that could result in benefit for either one of these two players. So if you think about this case, of course, you can see no player gets anything because you can see out of all three other choices, they could earn much more benefit rather sticking with here. That means our public signal should not say neither player has to pick this combination, right? This part we need to avoid. So basically it means a public signal should consider about only these three cases. So based on this signal, players should make a decision, and they are going to end up with one of these three. They have to skip this one. Since this has a symmetry, we can say, let's say, if this public signal result beta probability to pick down and left, ideally it should assign beta probability to pick up and right, because by doing that both players are going to have kind of a same payoffs, just flip. So if we have beta times 3 and beta times 6, similarly for the player B is going to get 6 times beta here and 3 times beta. That leaves 1 minus 2 beta probability to select this strategy, this combination, right? Now the question is, we need to find what is the value of beta. Since the goal is to find a correlated equilibrium such that the sum of the payoff is going to exceeding this 9, we can consider about writing a pair player A with the choice of beta for these two combinations, 1 minus 2 beta here. So he's going to get 3 times beta here, 6 times beta here, and 5 times 1 minus 2 beta from here. Since this is a symmetric matrix, so here we can say this is equal to UB. Then what we can say, UA plus UB is equal to 2 times this one, right? So we have 9 beta here minus 10 beta. So it means 5 minus beta is the expected payoff for one guy. So we have 10 minus 2 beta as the sum of these two. The requirement is 10 minus 2 beta should be larger than 9. So our beta should be less than half, right? Yes. Okay, with this simple setup, we can say our beta should be less than this. But is this the solution? No, this is just a part of a solution, because we didn't consider about the correlated equilibrium condition. That means deviation does not allow any player to improve the payoff, or deviation could result in a loss. Now we have to check that part. Without loss of generality, let's consider player A decide to deviate from the recommended strategy. Now, if you consider about whenever he was asked to stay in here, if he is asked to stay in here, he is not going to deviate, because if he is asked to stay in here, there's more since the other players are going to stick in here, he is getting payoff of 6, which is the best out of any 3 cases. So anyway, he's going to stick in here. So what could happen is, okay, whenever he is not, he is asked to stick into one of these two strategies. If he decide to deviate, so basically, let's say here, when he is asked to play up, it is known that the other player is going to be suggested to play right, and so the player A is going to get 6 points. Whenever player A is asked to play D, he doesn't know what has been informed to the other player, right? So he doesn't know whether player B is playing L or R. So in this case, like there are these two cases. Now, first we will find what could be the expected payoff of following the recommendation. So of course, we know whenever he is asked to play up, he needs to play up. But what we are focusing about, what happened when he is asked to play D. This is about A playing strategy of D. Now, if he follow this strategy, so he will earn 3 points with beta probability, because there's a beta probability that this is going to happen, and 1 minus 2b probability to this happen. So he's going to get, this is the expected payoff following the recommendation to stick with the choice of D. So we can say this will be 5 minus 7 beta. Now if we consider about deviating the recommendation. So recommendation is to stick with D, but he decided to deviate and play U. So there's a beta chance he is going to end up in here because of playing U, and because the player B is recommended to play L, and this guy is recommended to play D, but he decided to deviate. So they end up with UL case, which means no payoff with beta probability. And of course, there is the highest payoff 6 that could happen in 1 minus 2b beta probability, right? So here this result payoff is 6 minus 12 beta. Okay, what is the definition of correlated equilibrium? It says you deviating the recommendation result in a loss. So this following, you will get this payoff, deviating is getting this payoff. So in order to ensure correlated equilibrium, we need to have this condition. In that case, so beta should be 5, 6.1, 1 over 5. Okay, now we have a condition for beta. So in order to establish a correlated equilibrium, beta should be either equal or larger than 1 over 5. In order to satisfy the condition in terms of sum of payoffs, we need to have beta less than half. So any choice of beta in between these two values satisfy both conditions. It will be a correlated equilibrium, and the sum of the payoffs will be larger than 0.9. Okay, let's check another solution concept, a coarse correlated equilibrium. So this solution concept is much more generalized compared to both of previous, the correlated equilibrium and the Nash equilibrium. Here, all the players receive a public signal, which is quite similar to coarse equilibrium scenario. However, the difference is players decide whether to follow the public signals or not before receiving this information. So based on their choice, they pick the action. If they decide to follow the public signal, based on the signal, they will follow the action. But beforehand, if they decide to neglect the signal, public signal, and decide it is own action, he should follow that path. So formally, it is represented in this manner. So the right-hand side provides the expected payoff for following the probability distribution or the action profile. Then in the left hand side, this is about the payoff you receive by deviating the strategy. So it would be nice to see what is the difference between CCE and CE. Let's take the definition of correlated equilibrium. So things you have to not identify are these two main factors. The first thing is, if you consider about right hand sides from this these two conditions, you can notice in the correlated equilibrium, we are stick into certain strategy while other players change their strategy. So this is the expectation of following strategy Sn. So this is the expected payoff for following the strategy Sn. Whereas in CCE, you can notice this is all the choices that all the players can take together. So this is the expected payoff over entire strategies. So here expectation is over a given strategy, whereas here it is for the entire set of strategies. And the other difference, you can see it in the right hand side, left hand side. So in correlated equilibrium, this is the recommended strategy profile, whereas this mention any deviation from the recommended strategy. In post correlated equilibrium, here what we are using is the marginal distribution, which can be calculated like this. So here it means for selected action, the strategy Sn, we can calculate the marginal probability distribution. And this expectation in the left hand side is calculated based on this marginal probability distribution. To clarify this difference between post-correlated equilibrium and the correlated equilibrium, let's check one example. So here we have two players, A and B, with three choices. A has up, middle, down. B has left, center, right. So first question is to find all N's, Nash equilibria. Okay, maybe I'll leave it to you, although especially the mixed strategy Nash equilibrium, how to derive it, I'll leave it to you, but I can give you the solution right away. So if you think about the pure strategies, you can see if we, for example, if we decide this choice, basically player A doesn't want to deviate, however player B wants to deviate to improve its payoff. So this is going to valid for all cases where the payoffs appearing as 2, -2 or -2, because corresponding at least one of the player would prefer to deviate. By deviating, it can improve its own cost. Now if we consider about this -1, -1 strategy, of course you can easily see both players prefer to deviate from that strategy, because it will allow them to improve their payoff. So there is no pure Nash. So there exists a mixed strategy Nash equilibrium. It would be playing one of these action with probability of 1/3. So pick any choice with 1/3 probability. That will yield mixed strategy Nash equilibrium. You can try to formulate the problem and try to solve it. Now let's move to the problem, the second part of the problem. So here it says, show that these 6 choices. So if we consider these, it is up center, up right, middle left, middle right, so down left and down center. So which means the focus is about mainly these parts where one of player having payoff of 2 while the other is having -2. So neglecting these parts. Then it is said all these points have been assigned 1/6 probability. So notice that usually this public signal, when it is a broadcast, player A only sees what is intended for him, player B sees what is intended for himself, not to the other. So we can consider when there's a coordinator displays a certain public signal, player A and player B see 2 sides where the intention method only targeting the specific player. So the recommendation will say for the player 1, player A, play up, and for the player B, play center. However, A only sees this side. So he can see only the message saying, okay, you need to follow strategy U. So it can happen in 2 scenarios where B sees strategy C, or it could happen B seeing strategy R. But it is not visible to A. He only says, okay, he was asked to follow the strategy. Now the question is to show this approach is a coarse correlated equilibrium, but not a correlated equilibrium. Let's see whether this constitutes a coarse correlated equilibrium. So now, if you think about the suggestion, the definition of the coarse correlated equilibrium, it is about the deviation should not improve the payoff. So we can calculate the expected payoff of user A, which is going to be 0, because all these places has 1/6 probability to occur. If we consider any 2 of them, we can consider for the player A, this together they will make it 0. So in such a way, so we need to include this part as well. So such a way, the expected pay of agent A would be 0. Now, we need to consider the scenario where player A decide to neglect the public signal. Suppose at the beginning of a play, before he receive any public signal, the player A decide to stick to the choice of playing the action M. Now, you can see for the player for this action. Now we can consider about like 2 cases where player the central entity suggests to follow action U, or he just recommends to player to use action D. So if the player is recommended to follow same action, so of course there is no deviation. However, if any of these 2 occurs, we can consider what could be the payoff he is receiving. In that case, he is receiving okay, if he was following, let's say now A plays M. So This is his choice even before seeing the public signal. So if there's a like 1/3 probability that he is receiving a message U, and 1/3 probability he is receiving message D. In that case, if a message U has been received, in that case, since here the player already stick with the strategy M, then there's a like another 50% probability player B is received C to the signal regarding to playing action C, and another 50% probability to play action R. In that case, if the player has been playing C, the payoff would be -1, and if he was following the if he was received R, it would be -2. Yes, then divided by 2 and multiplied by 3. Again, the same thing can happen if the intended signal is for playing action D. So for that, we can consider again, it would be -1 -2 divided by 2 into 1/3 plus, okay, what would happen if the intended signal is to follow the exact M, then it will be 0, right? It is again 1/3 probability. So this says we have -1 -3 3 3, then it is the expected values become -1. So here is expected payoff of A once he deviate. Now we can see if the player A was following the recommendation, he would have received a payoff of 0. However, since he decided to neglect the public signal and stick with a choice beforehand, he ended up with having a payoff of -1. So this deviation caused him to lose the payoff. This is since this matrix is symmetric, choosing M, choosing U, or choosing D has no difference. So basically, it means player A should not deviate from the public signal if you want to not to lose the payoff. Same thing is applicable for player B as well. Now that concludes this proposed strategy of like signaling these 6 choices with 1/6 probability is a Coarse correlated equilibrium. But now the question says we have to see whether why this is not a correlated equilibrium. Now consider the recommendation is to play action U. So player A would see if he has been moved to playing D, he could improve this -2 to +2. So whereas here it is just a loss of 2 to -1. Therefore, he decided to jump to action D rather sticking with the suggested action U. So we know with following action U, it would result 0 payoff because these two are likely to happen, whereas deviation would result 2 with 50% probability and -1 with 50% probability, resulting half. You can see that deviation of the recommended signal allow that player A to improve its payoff. Therefore, this strategy suggesting 1/6, assigning 1/6 probability for these 6 choices is not a correlated equilibrium, but it is a coarse correlated equilibrium. Now let's move to the section where we now talk about learning rules. Previously at the beginning, we discussed about the problems, and at the this tutorial session, we talk about solution concepts. Now the question is how we can go from this problem to this solution concept. So this is defined by these learning rules. So the learning rule could be a kind of a mathematical logic or an algorithm, and this is the path to obtain a certain solution concept for given problem. For the first solution concept, we will be talking about fictitious play. So the fictitious play is about imagining or fabricating a certain concept and try to use it to achieve a certain solution concept. So this is kind of the simplest form of learning rule in arithmetic strategies. So here what would happen is one agent updates its belief about what others do. So here we don't assume they have access to what others is going to do, but just he try to maintain a belief about what other agents are going to do. Based on that, he tried to keep track of the frequency of what others did. So this is a history. Then he used it to decide his own strategy. So the idea is he pick a strategy that maximizes the expected payoff over the belief. So he assumes this belief is true for the future as well. So formally we can present it in this equation where this is the payoff of following the strategy by the interested player, and this is all the strategies that can taken by other players, whereas the player maintain a belief about this choice. So if he has a higher belief that these others are going to play this S minus n, he can put more weight in the payoff if we select this strategy Sn. So by considering all the choices of others, he can decide, okay, what could be the best strategy that he has to play in order to obtain the best payoff. Since this belief is kind of a keep tracking over time, so basically this could be we can see this as a time average expression of a belief. So it would be, when we go for certain kind of problems, it would be nice to have kind of a recurrent form of way of calculating this belief. So here what I did is this is the time average at time t, and what is the link between the observation at time t and the time average that has been calculated at time t, how it is going to be useful to calculate the time average at t plus 1. This expression is useful when you go for solving the problems. Now let's move to one exercise. Here, this is the game is called iterative matching pennies. So here there are like two players. They have two choices. Player A has up and down, whereas player has left and right, with different combination of payoffs. So you can notice that this payoff is a symmetric scenario. So at the beginning, it is suggested that to assume that player A believes as he believes that the strategy L will be played with higher probability compared to strategy R. So the belief is measured in terms of a weight. So he assigned 1.5 of weight to strategy L, whereas weight of 1 to strategy R. Similarly, B has a belief on a player A. So he has he assigned a weight of 1.5 for up and weight of 1 to down. Now your task is to calculate actions of each player for a couple of rounds. Now let's consider about what would a player A pick with these choices. So now let's consider player A. So he is going to calculate what could be the expected payoff playing action U. So let's say, what is the expected payoff playing action U? Since you know it is like 1.5 is assigned to left and 1 is assigned to right, he will be assuming there's 1.5 out of 2.5 chance to play left. In that case, he would receive a payoff of 80. Whereas there is 1 over 2.5 probability that player B is playing R, so he would receive a payoff of 40. Now similarly, he can calculate what is the expected payoff if he decides to pay down. So it will be 1.5 over 2.5 times 40 this one, and if a player B picks R with 1 over 2.5 probability times, it will be 80. Right now, if you consider about, okay, since these are common, I'll assign 3 here, I assign 2 here just to calculate. So you can see you have 240 plus 80. So we can write 320, whereas I can assign 3 here and 2 here. 120 plus 160, 280, if I'm right. Yes. So by just looking at these two values, this is just a rough calculation, but which will serve the purpose. We can see playing up seems to be more beneficial compared to playing down, given that the beliefs are 1.5 and 1. In that case, player A is going to pick up. Similarly, I guess since the weights are balanced, the equation this payoff is symmetric, player B is going to play left. Now, this is what happened at t equals 1. Now, when we go for t equals 2, player A, after playing this action, he has observed that player B decided to play L. So in that case, originally he has a belief of 1.5 assigned for left, and the player has used that same action again. I'll just go back and So, okay, this is the equation we would like to have. So lambda would be 1 over t plus 1. Then we can say 1 over t based on this one, right? Not the next one. So this is what we are going to calculate f at time 2 for L. So this is the previous belief, and this is the learning rate, and this action has been played this time, and it has been assigned 1.5. Yes, so by calculating this one, you can calculate the new weight or the new belief on the action L. Whereas for action R, he had a belief of 1, and this 1 plus 1. He didn't play this, and the previous belief is 1. So at least we can see it has been reduced to half. Whereas this has been reduced to 1.25. Yes, if I am not mistaken, yes. So we can see this has been 1.25, whereas this is now 0.5. Now, if we compare these two scenarios, previously the weights are assigned like, okay, 2 chances to play right, 3 chances to play left. Now, after seeing the first gameplay, now A changed his belief to such that he has assigned 2 chances to play R, but now he assumed that there will be 5 chances to play L. Now the new weights can calculate as like this. Similarly, you can calculate the new weights for player B and calculate the expected payoff based on new beliefs, pick new action, update the belief, and so on and so forth. So this is the iterative approach of how this fixtures play can be used. Next, we will check another learning rule, which is called regret matching. So here, compared to the fixtures play, what happened is, originally fixtures play was to, the goal of the fixtures play is to pick a strategy that maximize the payoff. In regret matching, what it does, instead of maximizing utilities, it decides to minimize a regret. So the regret is calculated as shown in this equation. So what happened is, let's say this is the regret is calculated for strategy I, SNI. So these are the payoffs that the player has received by playing different strategies over the course of time. This says what could have been the payoff if he was following this exact strategy. So suppose in the matching pennies use case, this would say this would have two choices, up down. If we are talking about the player A, this could have two choices depending of the time instant. He made one of these two choices, use it, and he get the payoff. But now this regret is calculated. Suppose assume that we are calculating this regret for the choice U. So what I did would say if we consider about the last example where A decided to play U at the first iteration, so he didn't he neglect this choice. But now in the after the after he has played this action, what he is going to do, he calculate a regret. Okay, what could happen if I played action D instead of U? What could what is what amount of the payoff I have lost because of this choice? So by calculating this regret, the player updates its a belief similar action selection probability with this equation. So he assigned more probability for the actions that caused higher regrets. So regret is okay. We could say the payoff would have been much better if a certain action has been played earlier. Then he assigned more regret, allowing the player to use that strategy more frequently in future. So let's try this learning rule with the same example as discussed earlier. However, in the beginning, it is suggested to use a regret of 0 assigned for all these actions. So player A assign 0 regrets. So he has no regrets of selecting up or down. So now the question is, okay, calculate actions of each player for a couple of rounds. So, for example, let's take the first round. Now, since player has no regret on his one of these actions, regret for U is 0 and regret for D is 0. So now we know we have to calculate these probabilities for these two actions. They could be exponential, no, just regret, right? So because I noticed that yeah, I think I need to mention this should be plus, yes, because you don't have negative regrets, either it is positive or 0. Otherwise this would be a negative rate, right? So you will be having 0 divided by 0 plus 0 probability, 0 divided by 0 plus 0 probability for action B. So of course this is not a calculated, it cannot be calculated, but we know since we have both equal weights, we can consider this as a 50-50 probability. Now, how this player is going to pick an action out of from here? So basically, it could be he could toss a coin and pick one of these actions. Suppose because of his choice, he ended up with choosing D. Whereas for player B, for his choice, he ended with playing L. So now we know the payoff of A playing D, whereas when the other player was using L. I think it will be yes of 40. Right. Similarly for B, player A used D, whereas he used the strategy L, so he got a payoff of 80. Now if we calculate the regret value, Of course, the action he has been played, of course, it is going to be no regret. So basically, regret for from the A side for action B is going to be 0, whereas the regret of B on action L is going to be 0. Now, what we need to calculate the regrets on the actions that have not been played. Right. In this case, go back to the equation. This says, okay, the action that has been played, and this is the action that could, the payoff that could have been played and earned a certain payoff. Now, suppose instead of D, if the player played U, he could have ended up 80. However, he got only 40 in his previous time slot. So since this is the first iteration, we don't have a summation and just the coefficient is 1. This is going to end up with as 40, a regret of 40 assigned for choice of U. Now, if we consider about from the player B's perspective, what could have happened if he has used R instead of L? So since A was playing D, if he has moved to R, he could have get only 40, whereas he already had 80. So this would result in a minus value. That is why I mentioned there should be a either this plus, the maximum out of a positive value, or 0, which is going to end up as 0. So now he has new updates for the regrets for the action, the strategy U. He has a regret of 40. For D, he has a regret of 0. Whereas for left, he has a regret of 0. And for right, he has a regret of 0. Now, based on these new values, we can go back here, calculate the probabilities, pick certain actions based on these probabilities, and iterative proceed this approach. And eventually, we end up with a solution where what could be the best strategy that player A would like to use, and what would be the best strategy that player B has to use. Okay, that's all for the this week tutorial. From the next week tutorial, we will discuss, focus about reinforcement learning. Thank you.